try that. Maybe that will work. That would be helpful. Okay, so last time we sort of left off on the phases. Does anybody know any of the phases? Solid, liquid, gas. Anybody know any other ones? Plasma, that's a good one. You don't really encounter that on Earth much. Well, that's not true. You yourselves, if you're encountering plasma on Earth, are probably going to be dead. So we don't really encounter plasma directly on Earth to the point where we could actually interact with it. Okay? Anybody know where plasma is generated on Earth? Huh? No, actually. It's not generated in Earth's core. That is a kind of unique place, though, because solids become much more malleable than they normally be. So, like, rock starts becoming a bit like putty in the core. But plasmas don't typically exist in large amounts in the core. It's lightning storms. Yeah, lightning storms generate a fair amount of plasma. And you can actually see the plasma sometimes in little bursts that aren't actually lightning. They typically burst a little bit afterwards. It's hard to tell, though, because our eyes are not exactly the fastest things in the world, right? All right, so liquids, again, they're going to have definite volume, but they do not have definite shape. How do you know they have definite volume? Have you ever seen your liquid? Is your liquid like spraying out the top of your containers because it's expanding to fill the whole room? No, and so it has definite volume, right? The volume's not continuously expanding or contracting, either way. Their shape, same as the container. The particle's going to move slowly in random directions. This is usually referred to as flow speed, but compared to a gas, it's moving very slowly. Okay? Gases, these have an indefinite shape. They have an indefinite volume. A gas will just continuously expand until it fills whatever container it's in. In the case of the atmosphere, that's basically the atmosphere of Earth, right? And so a gas will just continuously expand, diluting until it fills the entire Earth. And in fact, a little bit of those gas molecules escape every now and then. Did anybody ever think have you ever heard of like Starship Earth? No? It's an environmental concept for environmentalism. Or closed system. Anybody ever heard that? No. Anyways, Earth is not a closed system. It is an open system. We take in material from around us all the time. In fact, the majority of energy on the planet comes from the sun, right? So, the same shape and volume as their container, of course, for gases. The particles can be very far apart. This is molecular theory, in case you're wondering. And so they're going to move at very high speeds. They'll have very little traction with each other. It's kind of like when you guys are passing each other in that last minute in the hallway. You don't really have time to shake hands or do much, right? Because you're moving past each other at high speeds all over the place. Okay? Same thing for gases. All the stuff for liquids, solids, it just doesn't have time to do it. They're too far apart. They're moving too fast. Okay? And so you get very little interactions in gases. Now, molecular theory, you can think of solids. You have almost 100% of the interactions that are going to happen will happen. Okay? This is everybody's holding hands. Okay? And so it's very hard to shift things around because you'd have to break stuff to do it, right? Liquids, you can think of this as you have 80% holding hands, but 20% of those connections are getting continuously disrupted. Okay? And that allows things to still be attached to each other. It has a little bit of resistance. If you ever slap water, you've experienced this, or belly flopped in water. You've experienced this. And then that 20%ish broken allows rearrangements. Okay? Okay. All right. And then gases, everything's disconnected. They're all rearranging all over the place all the time. All right? They have basically no interactions. So let's identify the state of matter for each of the following. By the way, in the next slideshow, I'll have incorporated flickers, but I wasn't able to go back in this one and do it. Yeah. So identify the state of matter for each of the following. Vitamin tablets, eye drops. Vitamin tablets, what's the state of matter? Solid, you got it. Eye drops? Liquid, very good. Vegetable oil? Yeah, the oil version is liquid, of course. The shortening would be a solid. Yeah, like the Crisco. Yeah. Air in a basketball? Gas. Yeah, the air part is the important part of that, right? So vitamin tablets, by the way, what if I have those gel capsules instead, and they have that powder in it? Still a solid, isn't it? Just very small solid particles. Okay, very good. All right, so physical properties, these are going to be characteristics observed or measured without changing the identity of the substance. It will include the shape, physical state, boiling and freezing points, density, and the color of the substance, mostly. Okay. One of the things you can think of this is it's actually easier to define physical properties, and then chemical properties will be the other category that I'll be doing, based on the types of changes. Okay. So for example, if I tear a piece of paper in half, is that a physical property? Was its size, right? Because is it paper still? Yeah, it's still paper, isn't it? Yeah. If I burn the paper, is it still paper? Is ash paper? No. No, it's not paper. Okay, so copper has these physical properties. It's reddish orange in color. Oops, I forgot to do my little... Oh, you can see my cursor, can't you? Good, yeah. Yeah, because it's duplicate, not extended. Okay, so copper has physical properties. It's reddish orange in color, and you can see that right here. You'll notice that some of these places actually have color changes on them. That's actually a chemical change. Okay, that's that corrosion that's happening, right? Do you guys know what color the Statue of Liberty originally was? Kind of ish. It was a little bit lighter, more golden. But yeah, because it was actually an alloy of copper. Yeah, because they couldn't actually make very pure copper in the day, and you wouldn't really want to in that day. It actually was more structurally sound to make a form of basically brass-ish, but a little bit more pure, so it'd rust less. But anyways, why is it green now? Oxidation, yeah. Yeah, we've corroded the Statue of Liberty. And did you guys know that they were going to go ahead and fix that? And there was a huge outcry, and people were really angry. Yeah. So people didn't want her to be her beautiful golden self. They wanted her to be the green color. Yeah. Which, oh well. So again, it's shiny. It's an excellent conductor of heat and electricity, typically used for wires or like heat blocks and stuff, right? Yeah. Solid at 25 degrees Celsius. It has a melting point of 1083 degrees Celsius. Its boiling point is 2567. Anybody ever heard of ductile and malleable? Yeah? So copper is both ductile and malleable. Anybody know the difference? So ductile is, you're on the right track, but ductile is where you can hammer it out. And the easy way to think of that is basically you can make ducts out of it, right? So you can hammer it out, fold it around, and make like a building duct system. Okay? On the other hand, malleable means you can bend it. And those are not actually the same like property. You can be ductile and not be particularly malleable. For example, iron sheets. Iron can be hammered out into sheets. And yet if you take an iron wire and try to bend it a few times, breaks fast, doesn't it? Yeah. Physical changes are going to occur when matter undergoes a physical change of state, but its composition is going to remain constant. So for example, water can exist in the three phases or three states. That is ice, liquid water, and steam or vapor, right? And so those would be physical changes. One of the easy ways to remember this is physical changes are basically always reversible in some way, okay? Chemical properties. This describes the ability of a substance to interact with other substances. It'll change into a new substance when you're talking about chemical properties, okay? So for example, metals tend to oxidize and oxygen tends to oxidize metals, right? And these are chemical properties. When a chemical change takes place, the original substance will be turned into one or more new substances. These will have new chemical and physical properties. So they're distinctly not the previous thing, right? And so, for example, when you're taking breaths, when you fill your lungs with air, that's a physical change, isn't it? But when you breathe out, you've converted oxygen to CO2, haven't you? And so that one would then be a chemical change. Okay. All right, so during a chemical change, a new substance forms that has a new composition, new physical properties, and new chemical properties. Here's sugar caramelization because yum flan. Don't like flan? You ever had flan? Like homemade, actual, not the packaged stuff? And you still don't like it?
It's the texture.
Ah. That still seems like a you haven't had good flan thing.
No, it's like wet and I just don't, I'm not messing with it.
It shouldn't actually be wet. It
Oh,
should be like the texture of like cheesecake.
Oh, well, whoever made it in my AP pub class sucked.
Oh, sorry. Yeah, it should basically be like a thin crust of caramelization on a like almost a jello-y or cheesecake consistency. It's more like you ever had a truffle?
Like chocolate?
Yeah, the chocolate truffles.
Yeah.
It's like that.
That don't sound like Jello.
Like a it has some resistance to it, but it's easy to bite through substance. That's this part here.
You're not making it sound better.
Fair enough. You ever travel to Italy or Spain? Try flan, okay? Okay. You have to promise me.
That's my hat. I was like,
It's a commitment now. All right. So, iron nails, for example, they corrode in the presence of water. New substance forms on them. That's a red-orange powder. It's not always a powder, actually. It can deposit like a mineral would. We call that rust, don't we? And that's iron oxide, or Fe2O3. Does anybody know where the iron forms? Does it form where the water is? Or does it form at the surface? At the surface, yep. Because you need the exchange with the oxygen. The water itself actually protects it. So when you have things that end up in the ocean, they actually take surprisingly long to corrode. Yeah. Fully, I should say. Because as things get attached to them, that provides that exclusion surface. So let's classify each of the following properties as physical or chemical. Ice melts in the sun. Physical, very good. Copper is a shiny metal. Physical. So every time you go shiny, remember, physical change, okay? Physical property. Paper can burn. Chemical, exactly. Silver knife can tarnish. Chemical, very good. Magnet removes iron particles from a mixture. Physical, very good. Very good. Temperature. So this is going to be a measure of how hot or cold an object is as compared to another object. Remember, when we're talking about hot or cold, that is randomized kinetic energy. Okay? It's going to be measured typically using something like a thermometer. You can also measure it using the electrical conductance of a metal. So like when you heat the metal, the electricity takes more electricity to conduct through. Okay? Everybody know that? Anybody ever use your computer? It starts ramping up the fans. No? That's why. Because it's trying to cool itself. It's measured and reported in Celsius when we're using science, or Kelvin. Kelvin being the official SI unit, Celsius being the metric unit. Okay. Funny enough, I've actually seen more work in Celsius than Kelvin, despite that fact, which is quite amusing. Back in the day, it used to be reported in Fahrenheit, actually. Oh yeah. So if you go back less than 100 years, 80-ish years, you'll see a lot of Fahrenheits and stuff. Temperature scales. So the temperature scales that are mostly in use are Fahrenheit, Celsius, and Kelvin. Keep in mind that my lists of units that are in use is not even close to exhaustive. Okay? There's a weight unit in China, Jin. I don't even come close to touching all the units that have been used throughout history, okay? That wouldn't be possible.
What's a good conversion rate for Fahrenheit to Celsius?
Oh, I'm going to give you a formula in just a bit. The easiest way, though, is that's actually why this looks like this, where I have bars that go across like that, is this is one of the ways you can sort of help yourself remember, okay? And so in Celsius is very easy to remember, and that's the one I remember off the top of my head all the time. 0 degrees Celsius is the freezing point of water. 100 degrees Celsius is the boiling point of water. Yeah. And so that one's nicely easy to remember, nice and, it's linear and 0 to 100, right? That's always nice. Kelvin, because it has an absolute absolute zero Kelvin being the absence of random kinetic energy, okay? That one's 0, it has an offset from Celsius. And so it's 273.15 Kelvin is 0 degrees Celsius. Kelvin has the exact same distance for the degrees, okay? So 1 degree Celsius change is 1 Kelvin change. If you go up 100 Kelvin, you've went up 100 degrees Celsius, haven't you? Okay? And so these are highly related. Literally what happened is we did degrees Celsius, and then we realized there's an actual 0 that you could get down to. And we're like, okay, we need a new scale now. And Kelvin was born, okay? Literally, Kelvin was born, and he figured that out, and then it named Kelvin. Yeah. So degrees Fahrenheit is the off one. It's kind of the pain. If you're talking about the distance between melting and boiling water, it's 32 degrees Fahrenheit is melting water. Okay? That's the scalar offset of Fahrenheit. And you all probably kind of knew this, because what happens when it gets to 32 degrees, or 34 actually, usually your car does it. Your car usually goes ding, and then flashes. And it's warning you that there could be ice on the road, right? Yeah. And so 32 degrees Fahrenheit, ice. Okay? It corresponds to 0 degrees Celsius. When we get up to 100 degrees Celsius, this is actually a 180 degree Fahrenheit difference. Okay? So it's 212 degrees Fahrenheit. If we go up 100 degrees Celsius, that is 180 degrees Fahrenheit. This is actually one of the easier ways to remember it, because if you want to get into Fahrenheit from degrees Celsius, you take your degrees Celsius, you multiply it by 180, divide it by 100. Okay? And it's easier to remember things that actually exist than random numbers I give you in a formula. And so then finally, what if it's 0? What do I have to do finally? What's 0 degrees Celsius? 32 degrees Fahrenheit. And so I'd have to add 32 to that number, wouldn't I? Okay? Okay, don't worry. I'll sum it up in a formula. It'll be right after this. All right. So that right there is that difference in the degrees Fahrenheit versus degrees Celsius. I prefer remembering it 180 to 100 because it's something that's actually meaningful. Okay? But you can, of course, simplify it to 1.8 over 1. Oh, yes, definitely. By the way, folks, you don't have to actually ask me.
It's happening.
Yeah, it's okay. That's that Austrian military training being embedded in you. Do you know what the public school system was modeled after? Yeah, so it was factory workers, but they had to generate that from somewhere, right? And so what they did is they wanted to train their factory workers to be able to read the signs and basically show up to work on time, be able to read the clock, etc. And so they looked around in Europe and went, oh, this Austrian military school is very effective. And so they adopted the Austrian military school model to train their factory workers, which they got involved into this, which is the public school systems. The history of the public school system is so weird. All right. It makes so much sense, though, doesn't it? All right. So remember that you're going to take whatever degrees Celsius it is, multiply that number by 1.8, and then add 32. Okay? Okay. So, what is the temperature at which water freezes? 2, you got it. 0 degrees Celsius. What is the temperature at which water boils? 3, you got it. It took a while to do the math, didn't it? 100 plus 273, right? 373. How many Celsius units are between the boiling and freezing points of water? 1, because it says Celsius, right? What would be the Fahrenheit, by the way? 2. What would be Kelvin? Not 3. It'd be the same as Celsius. Because remember, every degree Celsius change is the same as Kelvin, right? So they're the same changes. So as long as it's a difference in, the degrees Celsius and Kelvin doesn't matter. They're the same. Okay? Fahrenheit's the only one that's weird. If you have changes, it's different. So again, this is that summary of the how to convert from the temperature in Celsius to the temperature in Fahrenheit. It's a fairly useful thing. If you're Canadian, you'd have this memorized already, and you'd used it like 20 times a day, every day, because their population is so heavily on the border with the United States that basically their temperature and weather reports end up being U.S. for most of them. So it gets kind of crazy for Canadians and having to deal with the U.S. imperial system. So this is the opposite, by the way. We've solved in this case for going from temperature of Fahrenheit to some temperature in Celsius. Is everybody okay with how that's solved? Does it throw anybody off? Okay. Remember your order of operations. So you have to subtract over the 32 first, and then you divide by the 1.8. Okay. All right, so let's go ahead and do it. The typical temperature in room is 21 degrees Celsius. What is the temperature in degrees Fahrenheit? Okay, so let me point something out. If this was a multiple choice question, and I'm giving you this as a multiple choice question on an exam, is there like a super easy way that I could deal with this question? What's room temperature? And
Whatever temperatures in the room.
yeah, it's, well, typical room temperature would be somewhere in the 78 to 72, right? Somewhere around 70. Okay? So if it's a multiple choice question and I see an answer, only one answer near 70, what would I do? I choose that. Do I actually have to do the conversion? No, not really. Yeah. So anyways, I see some people already did it. Fantastic. So we take that temperature in Celsius, right? We're going to substitute that into our formula. And so 1.8 times 21. This is then going to be plus 32. So what I end up getting is 38 plus 32, and this gives me 70.
Like if you're allowed to use a calculator on one phone, could you just like replace 2 for the 1.8 and then just like pick the closest one?
Yeah. Oh yeah. Oh yeah. In fact, overall, that's always a good thing to sort of run through your head, and then if you even have a calculator, and then you get your answer, sort of go, okay, this would have been like 40 plus 30, 70s. My answer on my calculator is, how the hell did I get 20? Right? Because sometimes you mess up the order of operation in your calculator, or the parentheses are not placed right. And so it's always a good idea to just evaluate and quick ball answers. If it's multiple choice, feel free. Yeah, yeah,
So
you
they're
very
not
much can.
like 0.1 off and stuff, like the answer choices.
No, that would be incredibly difficult for me to do. And not only that, but it doesn't really, like a lot of this is conceptual and being able to do the math. And so it doesn't actually behoove me to do something like that, right? Like, you obviously know what you're doing. The only time I would do something like that is if I'm specifically testing you on rounding. Yeah. Or like sig figs, right? I'd have different sig figs and they'd all be very close. So scientists have learned that the coldest temperature possible is actually negative 273 degrees Celsius. This is on the Kelvin scale. It's called absolute zero. It's represented by 0 Kelvin. This is why Kelvin doesn't have a degree sign, because the degree sign means arbitrary store point. Okay? Just like an angle would be, right? So your Kelvin scale, this has units called Kelvin again. There's no degree symbol in front of the Kelvin. There's no negative Kelvin temperatures. If there ever is a negative Kelvin temperature, what does that mean?
It's wrong.
Yeah, we've actually measured this wrong, or you've done the problem wrong. Considering the measurement versus problem.
Do we need to remember those formulas for the test, or are those going to be given to us?
You don't have to remember those. Yeah. The super simple conversions, but you get a sheet.
What do you need?
Like you get notes. You'll get notes
Like from you or from yourself?
from you. You can write notes. Yeah.
How big?
I mean, I wouldn't write a super amount of notes because it's not going to actually help you if you do that. Like if you have 10 pages of notes, you're just going to spend so much time looking stuff up that you're just going to miss questions.
More so, was it like a note card? Or
Oh no, you can just fully use a piece of paper or your notebook.
solid?
Yeah. Now, don't think that that's actually going to like be a no study. We'll have it right before we take the exam. We'll have a bit of review. But the biggest thing you want to do is get on those review assignments and then mail me questions if you have any issues, or drop by my office on Friday.
When is
Okay.
that exam?
It's going to be dependent on how quickly we cover material. And if it's getting too late, I'll have to start cutting things and move faster. But yeah, it should be sometime. I don't think it's going to be.
It was originally the 17th.
Yeah, it's going to end up being pushed back by probably one of our class periods.
So let's count on September.
Yeah. Once I start covering chapter 4, I'll give you a better time, okay? Okay, so again, there's no negative temperatures. The same size as Celsius, so 1 Kelvin is 1 degree Celsius and change. These are some different measurements to give you an idea of what sort of temperatures are where. Anyways. So again, the body temperature is above 41 degrees Celsius. This is called hyperthermia. This can lead to convulsions and may cause permanent brain damage. Heat strokes occur above 41.1 degrees Celsius. Your treatment may include immersing the person in a ice water bath. Anybody ever seen Pirates of the Caribbean? Okay. You know Jack Sparrow? You know how he's like shaking and does the weird things with his hands and can't seem to logically string together things? That's actually a permanent brain damage from a heat stroke because he was stuck on an island with no water.
You sure it's not jokes we didn't fire it?
No. In fact, it's kind of funny, but like pirates were actually not more likely to take drugs than the average person in that day and age. In fact, they were somewhat less likely to because they were stuck out at sea. And funny enough, pirates actually were not more likely to commit crimes than the average person. It's kind of a messed up thing. Like pirates were surprisingly egalitarian and had their own set of rules. But you have to remember the governments of the time were what we would consider incredibly draconic, and we would not be okay living under them. So, yeah. Like, you're not a noble, I can beat you. Why? Because I want to. Yeah. Like, the mafia literally was created because Italian nobles would just go into stores and take stuff, including, like, daughters and... Yeah. Yep. And literally it was revenge killings, and then the store owners would give them money so that they could go off and hide. Yeah. That was the mafia. They were like Robin Hood figures. Anyways, so hypothermia, this is the body temperature can drop as low as 28.5 degrees Celsius. The treatment involves providing oxygen and increasing blood volume. Typically, you do this using glucose or saline fluids. You would inject warm fluids at 37.0 degrees Celsius. Notice that's like a good body temperature. So you slowly warm the person up, but not too hot. Into the peritoneal cavity. This may restore the internal temperature, and so you slowly increase the internal temperature so they can regain function. So a person with hypothermia has a body temperature of 34.8 degrees Celsius. What is the temperature in degrees Fahrenheit? You have a dang degree Fahrenheit thermometer. How do I know what temperature I should be? Okay. How do I do this?
Multiply by 1.8, add 32.
You got it. Yeah. Multiply by 1.8, add 32, right? And so I go ahead and multiply by 1.8. I get a number in the 60s, 62.6 specifically. Then this is plus 32, and that's 94.6 degrees Fahrenheit that their body temperature currently is. Note that is not a normal body temperature. That is too low. Okay, so energy. This is defined as the ability to do work. This can be classified as either kinetic or potential energy. Kinetic energy is the energy of motion. Potential energy is determined by the position of an object or its chemical composition. Note that potential energy is energy that could be released, right? It's not currently being released. Kinetic energy, on the other hand, is released energy. Okay? Okay. So, water in a reservoir behind a dam has a potential energy. When the water is released and flows over the dam, its potential energy will then be converted to kinetic energy. Is that all potential energy was converted? No, it had chemical energy as well, didn't it? That was also potential energy. Okay? Let's think of another example real quick that'll more clearly demonstrate this. Okay, so we have gasoline sitting up on a shelf, right? It's in a little gasoline container. Okay? What happens if that gasoline container falls off the shelf?
There's gonna be kinetic energy.
There'll be kinetic energy released. Does the chemical energy get released? No. And so not all potential energy has to be released in one action. Okay? It can be. You could light it on fire and drop it off the shelf. But, all right, so let's identify the energy in each example as potential or kinetic. A, rollerblading. Likely kinetic, right? Where is that energy actually coming from, though, by the way? Ooh, I asked a difficult question, didn't I? So if we're on a hill, it was potential energy from the hill, right? Okay. If we're on a flat surface, the energy is coming from you, or your chemical potential energy stores, right? Okay. A peanut butter and jelly sandwich. Potential. Yeah, we could burn it. We could do all sorts of things, right? Okay. Mowing the lawn. Kinetic. Very good. Okay, now this last one, I'm going to have you guys actually do a flicker. Okay? Gasoline in the gas tank. So I'm going to call A, kinetic energy, B, potential energy. One day, I'm going to trip up well enough on these cords back here that I'll be gone for. Huh? Kinetic is A. B is potential. Okay. Did I get everybody?
Lucas. Lock in.
Okay. Okay, very good. Oh.
There we go.
Okay. We got it. Fantastic. Which one was it? Yep, it's potential energy because it's not currently being released, right? Now, if the car was driving, what is it? Yeah, we're starting to release that potential energy into kinetic energy, right? And how do we release that energy into kinetic? We go through combustion. Yeah. Very good. Now you know you've fully gotten into the science of it when finally you drop something today and you have a spill, and instead of cleaning the spill up or stopping it from spilling more, you're like, oh, finally a conversion of potential to kinetic energy. So, heat. This is the energy associated with motion of particles. The faster the particles move, the greater the heat or thermal energy of the substance. It's actually randomized kinetic energy. The mass of the particles also plays a part of this. For example, if you get vibration at the same speed of something with higher molecular mass, that means you're using more energy, right? Or it has greater heat energy. The SI unit of energy and work is actually the joule, and that's denoted by a capital J. 1 kilojoule equals 1,000 joules, which you all probably remember from the prefixes, hopefully. This right here is a different comparison of energies right there. Right here is the energy in the sun in 1 second. As you can see, that's an absolutely massive amount, right? Yeah. We only collect a very, very tiny amount of that energy on the planet. So.
All of my face.
Yes, indeed. Are you You still experiencing sunburn, or are you good?
Just a little bit, yeah.
Okay. Have you tried Aveeno on it?
I have actually.
Okay.
I put aloe on it.
Aloe doesn't work very well, but Aveeno works great. Yeah, if you cover it in Aveeno, I've had like 3rd-degree burns from 12 hours of sun exposure.
Okay, well, I was only just 3 hours,
So I actually, that's why I got a tan that like a week and a half ago, is I was out under the sun for like 4 hours, and I went home, Aveeno all over, despite the fact that I haven't been out in the sun for. Yeah, it really, really helps. By the way, it works great for any burn, period. Yeah. Yeah, it kind of is.
Are you endorsed by?
No, it's what I keep to help people with chemical burns because it works.
You should ask me to.
Yeah. I should. I would just do it for the free Aveeno because the amount of chemical and burns from like Bunsen burners and stuff that I have to treat, and then I can never seem to justify that as a lab expense.
Do it.
Like, it would actually be a significant improvement in my life. Yeah. Good idea. So the unit of calorie. Has everybody seen calories before? Yeah. I've obviously seen calories.
Stop it. Don't say that to yourself.
So, I do love myself. That's why I recognize that I really, really do need to burn calories. Yeah,
You're burning calories right now.
that's true. Surprisingly, lecturing can actually be fairly challenging to some parts. This is defined as the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. So literally it is, if you took a gram of water, you had 1 calorie, it would increase that temperature by 1 degree Celsius. Okay? It's not exactly a huge amount of energy, is it? No. Calories is actually a fairly small amount of energy. 1 calorie equals 4.184 joules, and this is an exact number, which is, you're probably going to forget. Most people do forget and just do 4 sig figs, but it actually is an exact number. It's a weird exact number, but it is. Okay? And that's because one has actually been defined off of the other. Right? 100 calories, or 1,000 calories is the capital C calorie, which is a kcal. Anybody ever seen the back of the package? That's the capital C calorie, isn't it? So they're kind of lying to you. It's actually a kilocalorie on the back of packages. So all those numbers they're giving you, multiply by 1,000.
Wait, so then when we multiply the daily intake by
Yes, it wouldn't affect you. Yeah.
Wait, so in like 1 Coke can, there's enough energy to raise
Oh yeah.
the heat of a gram of water by like
Thousands, hundreds of thousands.
calories.
Hundreds of thousands of degrees. Yeah. Yeah. First off, like soda in general is just such a massive amount of calories that, like, basically it's a meal. Like, there are many times in history where that would have been like, oh my goodness, you just foraged for 8 hours for that. Sodas is ridiculous. And overall, like, American diets have so much more sugar in them than it even begins to make sense. Like, that's one of the reasons our health has not improved like the rest of the world has. We're like living 5 to 6 years less than we should be just because of food in the U.S. Does anybody ever heard of the food pyramid, by the way? Okay. What's on the bottom of the food pyramid? Carbs. What's the main component of carbs?
Energy.
Carbohydrates. What is carbs used for in your body?
Energy.
mostly energy, but other things as well, like making DNA. How many carbs do you need in your diet?
A lot.
Are there any essential carbs
Bread.
that you can't make?
Probably.
No,
Soda.
there's none.
So I don't need to eat carbs?
No.
Don't tell me that.
Yeah. You can go an absolute zero carb diet without any health effects at all. It's not really a life worth living. But physically, you would have no negative effects whatsoever. That's why people going on like carnivore diets have such an easy time of it. Whereas on the other hand, if you go vegan, most vegans actually mess that up the first time they try it. And most vegans mess up their diet the first time they try vegan.
Why?
Because you have to do a lot of research, because it's very hard to replace proteins, and there's actually necessary fats that you need for your diet. You can't make them. There's essential fats. And so it's so much harder. Yeah. It's possible. It's very possible. You can go vegan, of course. But most people do it wrong the first time and have huge health effects.
Yeah, I'm
Yeah.
vegetarian and I definitely like
Yeah, it's very hard to do, right? Like, you have to really plan things out and think them through. It's not... Me?
Yeah.
No, I've never gone vegan. I know vegan really well. Huh?
Keto.
Keto? No, I've never done that either.
I've done that.
Any extreme diet is not really a great idea. Though overall, cutting out carbs and sugars from your diet is an overall good idea.
No sugar?
No, you can have sugar, but just don't have extra processed sugars. That's always a good idea.
So
Remember
everything,
that high fructose corn syrup?
Yeah.
is it everything?
Yeah, unfortunately in the US, it kind of is. It's very hard to do.
So
But
what happened with Italy for that?
if you're in Europe, it's really easy to do. But you can do it in the US now.
So,
You just need to avoid going to places like Walmart and fast food.
Just avoid. I love Trader Joe's anyway.
Yeah, yeah. Trader Joe actually has some decent food, though they also have not decent food. By the way, does anybody know why grains were at the bottom of the food pyramid? No. The bottom is the thing that you need to eat the most of on the food pyramid. Yes.
You need to eat the least of them.
So in reality, you needed the least of those, but the government said you should eat the most of those. Nope, it wasn't healthcare. Before the food pyramid, we had a farm subsidy for corn production.
What does that mean?
And that means they just paid people to make corn. And they got tired of that, and there was a bunch of political backlash.
Isn't corn like not good for you?
It can be good. Actually, it has an essential fat in it. And so there's actually are health benefits to corn. The problem is they make a lot of like stuff that is bad for you from the corn, because corn is one of the things you can grow all throughout the US, and it provides us a tremendous amount of food safety. And so it is actually a positive thing to have excess corn, because you can dry it out, you can preserve it. If we ever have it, like, that's why we've never had a real food shortage where people die from it in the US. Even during the Dust Bowl, we did not have it. Is because corn, essentially.
There, you gotta go on an all corn diet.
No, no.
but
But
I drink ethanol.
that's actually why the food pyramid went away. Is they started using ethanol in fuel. And so you can make ethanol from
Corn.
corn. By the way, 14 nutritionists had their careers destroyed. 14 of the best nutritionists of their day because of the food pyramid. They came out against the food pyramid and were blacklisted.
Why do you know so much about this?
Because I just know a lot about like biochemistry, health science,
You should have just said because I know a lot. 'Cause you know.
I guess. Anyways, interesting little factoid. Does anybody know, comparing an egg and Lucky Charms, which has a higher health score on the today's Lucky Charms? Yes. Yeah.
What is more healthy about Lucky Charms
It's not. It's not. Yeah, the government's website is just not really well thought out. I don't know why that happened. It could be a little of each. It's rarely all, like, you don't need to directly pay people. So actual outright bribery is pretty rare. You just don't have to, because they're in such an isolated position where you can influence them by putting people next to them that most politicians and career bureaucrats, they're not being bribed. They just don't know better because all the people around them tell them one thing. So, anyways, it's let's get out of politics. You guys can go into politics and do that. Carbohydrates, again, these are one of the body's primary sources of energy. That is the positive of carbohydrates, is that your body, in terms of energy, can use carbohydrates extremely well. Your brain actually only uses carbohydrates. So, but you can make all your own carbohydrates. You do not actually have to ingest them.
So if I eat more, does my brain work better?
Temporarily, yes. In fact, on testing, if you eat a small candy bar, one of those little fun size, before you do the test, the average improvement in scores is about 4%.
Okay, so
Yeah. The king size doesn't help you. So, your primary fuels tend to be things like carbohydrates, and these are your more short-term energy, and you tend to burn through them faster. Okay. What happens is you usually have to fix these in a longer-term energy that's more dense in its energy form, like fats. Okay. And that's why we carry fats around with us. We carry fairly little carbohydrates around with us. Okay. Does anybody know we carry carbohydrates around with us? Glycogen? Anybody know where that's located? Yeah, it's your belly fat. That's why it's one of the hardest things to get rid of. Yeah. So like, here, my belly fat. I definitely have it. So like a beer belly, that's the reason for a beer belly. It's a lot of glycogen storage, carbohydrate storage. Okay. You also carry a very thin skin usually around many of your muscle groups, but it's not the jelly thing you're thinking of when you're thinking of fat. It's harder, okay, because it's not fat. Fat, on the other hand, is the majority of your energy you carry around. Does anybody know why you would carry around energy in the form of fat?
So that, like, if you aren't eating for like 12 hours, you don't just die.
Yes, but why don't you just carry it around as glycogen? Plants do it. They don't fix it into lipids. They actually carry it around as starch.
Because we're better than plants.
We aren't. We're the older, less evolved species that has less chromosomes. Plants have more chromosomes, more DNA, about 10 times more DNA matter than us.
Low-key, though, I think I'm beating the plant in the fight.
The plants are far more evolved than us. The reason for it is plants don't have to run around, do they?
Nope.
And so they can afford to have it take up a bunch of space, be stiff, and not be mobile. Okay? And they store it typically in their roots. That's why the roots are white, they're starchy. And that's why they're sweet if you eat them. On the other hand, if you need to move around and run away from things because they're going to try to eat you, you need it in the form of fats because they're much more energy dense. Okay? Yeah. Proteins. These are the next one. We typically don't use these as energy as much. We can, but we don't use them as energy as much. Anybody know why? Because this is what we make all the stuff that actually does stuff in our body out of. The amino acids from the proteins specifically.
So then why did Jim Bros eat so much protein? So then why did Jim Bros eat so much protein?
Build muscle. Yeah, he's getting in the building blocks to build his muscles, and it provides fairly low energy in comparison to that. Yeah. Whereas if he'd done a bunch of carbohydrates and fats, he wouldn't have all the amino acids he needs. and he'd be taking on a bunch of stuff that would end up being converted either into glycogen or fat in his body. And he wouldn't have gained muscle instead. He would have just gotten really big. Yes. Actually, do you guys know after DNA, what the next biggest determinant of your lifespan is? Genetics DNA is number one, but what's the next biggest? Resting muscle mass. That's, yeah. Yes, big time. And it also is correlated with IQ. If you want to improve your IQ, the easiest way to do is just start exercising like 30 to 45 minutes a day. A healthier body can support your brain better. I myself am guilty of not doing this properly. Thank you. So here's a food label, of course. The capital C calorie is a kilocal. That's 1,000 calories. Here we see some snack crackers right here, and we see the different breakdowns. Everybody good with that? Okay. This is actually how you measure this, by the way. It's called a calorimeter. And what you do is specifically this would be a bomb type calorimeter because it has an insulated container around it. And what you do is you actually burn the substance in there with oxygen, enough oxygen to burn it. And then you collect up all the heat and see how much it raises the temperature of this known amount of water in there. Okay? And they've done this for all the different foods and substances. Some of the back of the crackers and stuff are actually abstractions. They're just adding up the different amounts of substances in them to get those numbers. But overall, that's how you do that. Okay?
So how do they know like what amount of carbohydrates is in there, what amount of protein is in there?
Oh, it's a fairly so nowadays it's a fairly simple test. You can actually take these and submit them to a lab, and what they literally do is they just take that substance and then they grind it up, process it, and then they test how many carbohydrates there would be in it, how much protein, how much fat. You don't really have the science right now for me to go too much into the testing, but we can a little bit later. Actually, we'll understand that better.
How do they determine the serving size?
The serving size is just a random.
I'm just gonna make the number look best for them.
Yeah, oh yeah. That's why like Oreos is like 2 Oreos. Nobody ever eats 2 Oreos.
Or like they'll give you like one of the normal size things of Skittles, and it'll be like 3.5 servings in a package. And it's
Yeah.
like, who's eating
Or like
a third of a Skittles?
a
package?
Snickers bar, right? Who's gonna take off the wrapper for it and then not eat it in one go? Like, how the hell are you gonna store it? Who's storing their Snickers bar? And yeah, it's not one serving, is it?
In my holiday.
Yeah, those numbers are usually just pure BS. They have nothing to do with anything. Some of the more ethical companies will actually do, like one serving is actually what they expect people to do. Yeah, and they'll like provide a little cup scoop and that's one serving, right? Yeah. But yeah, a lot of companies, it's such a BS thing. You guys know candy bars were actually meal replacements, right? They were like the protein bars of 1930. And they were very high calorie because in the 1930s, most jobs were physical labor. Yeah. And so like Snickers and those things, good Mr. Goodman, Good Bar, those things were actually like save people from being starved to death because they're very cheap. So the energy values for the 3 food types are going to be given in kcals per gram. And there's the kcals per gram. This is for carbohydrates, this one's for fats, and this one's for proteins. And you can notice that the carbohydrates and proteins are actually pretty similar in kcals per gram, aren't they? That's called low density. Okay? This one's much more dense, isn't it, in terms of energy output. Okay? And that's why the fuel we store is in that form. Anybody know the problem with going to renewables right now?
Renewable what?
Renewable energy. It's very low density. Like liquid fuel you can put in your car, gasoline, very high density in energy output. Batteries, very low density in energy output. It's a lot of weight to carry around for that energy output. And so technology is starting to catch up, though electric cars are actually the older type of car.
And they suck, because have you seen those lithium lines?
Yeah. Oh, yeah. That's a whole nother discussion, and you're exactly right. The lithium and then the material for the tires, the motors, those mines are even worse, which is just wild. Yeah. Like the ethical ramifications of what's going on is just crazy. But anyways, a cup of whole milk contains 12 grams of carbohydrates, 9 grams of fat, and 9 grams of protein. How many kilocalories does a cup of whole milk contain? Let's round off the answer for each food type to the tens place. Okay. So what we need to do here is we're going to have to do what do we have, what do we need, how do we get there, right? And so what do we have? Well, we have 12 grams of carbohydrates, 9 grams of fat, 9 grams of proteins. What do we want? Kilocalories, or capital C calories. And so all we have to do then is multiply these numbers up here by their kilocal per gram. This one being 4, this one being the 9, right? There. And the last one being the 4. Okay. So, again, this is that summary of that information we just talked about. Let's go ahead and do it. So, carbohydrates, we have 12 grams. It is 4 kilocals, or capital C calorie, per gram. And that's going to give us 50. 9 grams of fat times 9. And so we're going to get, technically it's 81, but we went ahead and rounded that answer right there. You shouldn't actually do that before you're done with your math, but oh well. 9 grams times 4, and that would give us something just below 40. It would round to 40. We go ahead and add those together. That'll give us our total energy, and that's 170 kcals. So when I drank that milk, how many kcals did I intake? 170. Yeah. How many should I take in per day? That was kind of a trick question. Your daily intake is based on your weight, though it should actually be based on your muscle mass weight, not your... Yeah. And the weight of your bones also would factor into that, because you're having to move around more weight. But anyways, yeah. Me, I should probably be taking 1,500 in because I'm so sedentary. Because I sit here and lecture, right? But I am being nice to myself. I probably only burn 1,000 calories a day. I mean, I'm sitting here lecturing you guys all the time, right? I have to like run around and lecture, and that would be weird.
Do we need to remember that, like, that second number where it was like the
4
kcal per gram? Is that something we were supposed to like?
Now, honestly speaking, as a human being,
I need my test.
not for this class, you really should remember this number.
But like from the test. Like, am I going to be given that question? I'm going to be expected to know what the 4 kilocalories.
Doubt. Well, first off, you have notes, but I would doubt that I would actually ever ask a question like this and not give you guys that number. I don't envision that.
Please give me the number.
But I mean, it's not exactly hard. They're all 4s except for fat.
Oh, really?
Yeah. Carbohydrate is 4. It's only these 3 things.
Well, like, okay, cool. Why didn't we know it was this exact question? But like,
Uh-huh. Which one? Oh, yeah, sure. Yeah.
I had no idea that.
No, you never have to remember these numbers. Yeah. if you ever needed these numbers, you would use the conversion factor to get them. And so that's times 4. Okay, so the number of kilocalories, by the way, you can always find this slideshow online. It's linked to your Canvas website. The videos are uploaded to the YouTube channel. Okay. Let's go ahead and look at losing and gaining weight. So these are the number of kilocalories or kilojoules that are needed in daily diet of an adult. It actually depends on a number of factors, gender, age, level of physical activity. And so, for example, you can see females 19 through 30, really helpful for you all, since you're all below 19. But know that if you follow these numbers, you'll be losing weight because you'll burn energy faster. Okay? Well, then don't. Seriously, there is no target weight you have to reach. I'm not actually fat shaming. I'm teasing you guys with myself. Now, admittedly, like, there is a exercise goal that you should have. If you can't run for about 5-10 minutes, then you have a major health problem, okay? And you're going to have massive negative effects. It doesn't matter what weight you are. If you only weigh 100 pounds and you can't run for 5-10 minutes or do some sort of physical activity on that level, forget legs, I don't care about that. You really do have like a future of bad health coming. And I mean really, really massively bad health, okay? My health actually took a massive dive down because I had to drive back and forth between Iowa and here like every couple of weeks. And yeah, my father got committed and I had to do a bunch of stuff. But I'm not going to go into that. That was really crazy. Yeah. Oh, I've had so many nutsy, like just wild things happen to me. I've been jumped by a gang before, multiple times. I technically was the other party of what would called a gang fight. Me versus a gang. I was sent to a school with a really bad gang problem where the mayor's daughter had her legs broken for money. Yes, and she refused to pay and they broke her legs. And they sent me into that school with a $130 pair of shoes. I had been trained since I was 5 by a world champion in martial arts, Homo Maka, who was one of the only 8-dan Taekwondo, 6-dan Aikido, 6-dan Jiu-Jitsu in the United States of America. He had his end of career when Chuck Norris was coming up and kicked him out of the ring. That's not really a fair fight, by the way. But, yeah, he was a badass. The time against 3 people, yes. Yeah. Yeah. That one I very much won. That group stopped bothering me. They never bothered me again because I slammed him into a locker 10 times and he couldn't stand up again. But don't do any of this because, like, this is not okay. They should have stopped this entire thing from happening. That was just nuts. But the time against 8 people, I walked away. I would count that as a win.
Were you unscathed?
No.
No, it's not.
You can't fight 8 people and not get just
Why were they jumping
wrecked.
you?
They wanted my shoes.
Both times?
The first time they wanted my shoes. The second time, I don't know if it was just like because I beat up that first group and like they had to assert dominance or what, but
Did you walk away with your shoes?
I did.
Oh.
Yeah.
That's a W.
Oh no, nothing ever got taken from me.
What were they? What were the shoes?
They were Nikes.
Okay.
Yeah.
Those
They were very nice Nikes.
How do you win against
Positioning. You get into positions where only 1 or 2 people can approach you at any given time, and then honestly, the taekwondo and striking isn't as helpful. What you do is you have to grab them, one person, in such a way that you can maneuver them into another person and not let anybody behind you. And that's why I didn't walk away unscathed. When I was moving and throwing people into another person, people sometimes would get in and hit me. And yeah, anyways. Keep in mind though, because I've been training since I was a child, like when I was 7 years old, I could leg press 400 pounds.
Oh, what did you just say?
I could leg press 400 pounds as a 7-year-old. And like I was invited to nationals every year. Like you can accomplish some great things. I'm a burnout, in case you're wondering.
Where did you get there? It's like, where did all this take place?
So the gang fights took place in